In this video, we are going to talk about an operation on a binary search tree, which at first may seem relatively straightforward, but ends up being a lot harder than one might realize. So, when we have a binary search tree, we realize that everything to the left is small and everything to the right is bigger, and that is recursively true throughout the tree. And when we're going to remove a node, we have to make sure that we do not violate the structure of the tree, that idea that everything to the left is small, everything to the right is bigger. So for example, if we wanted to remove a particular node in here, like a 3, well, that'd be easy. We just get rid of the 3. But the problem really comes in when we have children, and there are different cases for different situations. But before we begin, I want to remind you of a subtlety that a lot of people overlook, that we have to account for multiple values in the tree. So if we have a binary search tree, what we do is we draw a line and we'd say that everything to the left is going to be small and everything to the right is going to be large. And I've intentionally used that big, small, because we haven't considered the idea of we haven't emphasized the idea of multiple values. So what would happen? What would we have if there was 6 or 7 10s in the tree? Now, up until now, you're probably thinking this is smaller and this is larger, but we have to know what to do with repeated values in the tree. And so for this, we would have to take an example of what do we do with the larger nodes. So what we have here is we have a trichotomy axiom. This is smaller, this is greater. What do we do? For our convention, in this implementation, we will say that all of the repeated elements would go to the right. To emphasize that then, take a look at this tree here, and you can see that there is 2 10s in this tree, and for the 2 10s, the child 10 must be in the right subtree. And then if we would insert a 10 again, well, where would that have to go? We'd get down to this 10 and we say, oh, equal values. Do the equal values go to the left or do they go to the right? They would always go to the right. And if we had to add another 10, it would be on the right side. Now, it may not seem like an important concept, but when we remove nodes from the tree, that is going to affect how we do it. All right, so when we are going to remove nodes from the tree, we have to make sure that we account for the structure of the tree and we do not violate the condition of the tree. The first case is if we want to remove a node that's a leaf. If we want to remove a node that's a leaf, and by a leaf we mean it has no children. That's the most straightforward case, in that if we wanted to remove a 6, all we have to do is get rid of this and set the parent's left pointer to null. The parent's left pointer goes to null, and then we've removed the 6 from the tree, and everything stays the same. When we're done with removing the 6 in this case, we're done, and we have everything. Now, another case is if the node that we want to remove has only one child. Well, with this, we call it an elbow if you have only one child. Well, here's the elbow that would be bent, and for example, 36 has only one child, and this is like an elbow. It's just that the elbow isn't bent. In any case, 30 is an elbow node, and 36 is an elbow node. 35 is not because it has 2 children, and 38 is not because it has 0 children. So in each of these cases, let's say that we get to the node that we want to remove, and we find out that it only has 1 child. So the node that we're wanting to remove, in this case 30, this has only 1 child. Now we can't just delete it, because if we delete the 30 and have 40's left pointer set to null, then that's not going to work. Then we're going to lose all of these values here. So if the node that we want to remove has only one child, we can see that, well, we want to remove this. And 40 still has to keep track of and account for this. If we just have 40's left pointer and we just set 40's left pointer to its grandchild, it has only, if node 30 that we want to remove has only one child, then that means that 40's left has only one left grandchild. So then you take 40 and you'd point it to the 35, and you have to think about this. All these then move up, get promoted up. And then we would delete this node and just bypass it. And that's the idea there. We still need to have all of these values in the tree. That one's not too bad. So in the case that we find the node that we are looking to delete, we ask ourselves, does it have 1, 2, or 0 children? If it has 0 children, we just delete it. If it has 1 child, then we just promote its grandchild to the child of the parent, and then we're done. But unfortunately, we have a lot of work to do if we are going to remove a node that has 2 children. And that is our case 3. What if the node has 2 children? So in this case, we want to remove the 90. And for this, we're going to remove the 90 from the tree. You say, oh, okay, well, maybe I could just take the 60 and have it point to the 96. Well, the problem is the 80 and the 70 then get left out. So you say, well, okay, maybe could I have the 60 point to the 80 and the 96? No, that's not going to work. So it ends up being a relatively difficult problem, because if we chop off 90, now we have 2 subtrees, and 60 only has 1 right pointer. So we're going to do this in a couple of different steps. The first thing that we're going to do is, this is the node that we want to delete. So we found the node that we want to delete. We find out that it has 2 children, and so we silently curse under our breath, but we forge ahead to do the rest of the procedure. We ask ourselves, if we don't change the structure at all, then what value could go in this 90 spot and still have the conditions for the tree to be held, for the binary search tree to be held? Well, you could either take the maximum of the left subtree, or you could take the minimum of the right subtree. However, this is why we emphasize that idea of repeated roots. There might be some repeated nodes in here, some repeated values. So given our condition that there might be repeated nodes in here, what we're going to do is we're going to look into the right subtree. So the node to be deleted's right subtree So in that right subtree, and we are not going to mess around with any pointers. We're not going to stitch together any pointers. We're not going to mess with any of these 3 pointers. Instead, we're going to change the value of this node 90. So what we're going to do is we're going to look and we're going to find the minimum value in this right subtree. So when we go through, how do we find the minimum value? Well, we look down and we start here, and to find the minimum, we go left, 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 until we find a node that does not have a left child. So for this then, we go down, and in this case, the minimum is 93. How do we find that? Well, with that 93, it's going to be the left, 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 until we find a node that does not have a left child, and then that is by definition the minimum in that right subtree. So we find the minimum. the min value is equal to 93. So you might say, okay, now what do? We do not monkey around. We don't try to pull this 93 up as the child. Instead, what we're going to do is temporarily have 2 copies of that value. We're going to overwrite the data of this node. Again, not changing any pointers. We're going to overwrite that data. And then down in the right subtree, you'll notice, wait a minute, we didn't have 2 93s. Now we do have a 93. We have to do something more, okay? So what we're going to do, and this is really beautiful here, we are going to then, now we called remove 90 on the root, but now we're going to call remove, not 90, remove 93 on this subtree. So we overwrote the value 93. Now we need to get rid of the 93 in the right subtree. How do we do that? We've already got a function for that. We've got the remove function, so we're going to call it recursively. Now you might say, well, that doesn't help us, because what if I get into this situation and I get case 3, 2 children? If we have the minimum value in the right subtree must either be a leaf or an elbow. Because if it were not a leaf or an elbow, then it would have 2 children, and then it would have a minimum. As long as it has a left child, the left child's going to be smaller. So if we recursively call on the right subtree, then we're automatically going to be covered by either a leaf or an elbow. And that's what we're going to do for that. So that's how we remove. And so when we're writing our code, we always need to make sure to check the 3 different cases. Is it a leaf? Is it an elbow? Or is it a node that has 2 children? I'm using this term elbow, but even if it doesn't look like a physical elbow, what I mean by case 2 is an elbow, it means it has 1 child. So it has 1 child. This looks like an elbow, but if it has only 1 child, then remove is relatively easy. If it has only has 0. So if it's a leaf, it has 0 children. If it is a elbow or a stick, then it has only 1 child. And then remember that this 2 children, that's going to be the difficult case. All right, next we're going to do some type along so that you have a bit of preparation for your in-class exercise.